So I know we try to make this a sort of a lightweight presentation to be suitable for an annual meeting where people don't really come for, having their brains picked. But unfortunately, I sort of overdid it a little bit, so there will be some equations and stuff. But let's keep it lightweight. And I both did over-prepare and under-prepare this presentation in the sense that I over-prepared all the equations and under-prepared the pedagogical aspects of it. But let's have an open discussion. So the idea here is that, okay, stable diffusion and all these generative models, they're making the news, and I think it's really transformative in a sense. And everybody I'm expecting. You have seen, like, you can write something and you get a picture, or people making amazing pictures, or changing, you can even start making videos and so on from these things. So, but we are machine learning engineers, or we're an AI association, so we want to know how this stuff actually works. So that's the purpose of this presentation, to go into the details about how the algorithm is, what it's actually doing. And instead of explaining like I'm 5, it's explaining like I'm a machine learning engineer. But the picture I generated with Stable Diffusion is a 5-year-old machine learning engineer learning mathematics. That's the prompt that I chose to make this best picture. But it's really funny because you can see this poor kid and his leg, like what's happening with that. And also the computer is a little bit strange, like is it 2 screens, 1 screen? And there is some strange things happening with the keyboard. So these models don't really have a reasonable sense of reality, but still they work quite nice in certain cases. Maybe we can determine why that is. I will make this maybe half an hour or something like that. I think that's suitable. So, I don't know if you're keeping up with what's happening in AI recently, but diffusion models is the big thing since this year and late last year. So I don't know if you remember when transformers came in 1819, and you had this paper like attention is all you need, which sort of transformed natural language processing completely. Natural language processing hasn't been the same since. And we're claiming now that diffusion models is the same thing, but with generative models and computer vision. They are now the state of the art in image generation, beating generative adversarial networks, for sure, since a couple of months. Taking the world by storm is how the State of AI report is phrasing it. And I have a screenshot from the State of AI report. I don't know if you know that one, but they put out a report every year on what's happening in AI, every recent development. And in their summary, they say that diffusion models is taking the world by storm. So is this a transformer moment? Will diffusion models change computer vision and generating images and so on? Definitely. And I definitely think so. What's happening right now in just the last couple of weeks or last couple of months, it's crazy. So hopefully we get a little bit of better idea of what's going on after these 30 minutes. That's anyway the point. And learning a little bit what's going on under the hood. So let me see if there is something interesting to say here. But you have this DALI 2, Imagine, Stable Diffusion. Some technical details. So let's go through them later. But the agenda is basically to discuss what's actually the point with diffusion models, how they work when you condition on text, when you give them some text to start generating a picture from. Stable diffusion is an example of what's called a latent diffusion model, so we'll briefly discuss that. And very briefly discuss diffusion models versus generative adversarial networks, which is sort of the state of the art before these came up. And this is why I underprepared it, because the agenda is not actually true to the slides. But so the timeline, I think, is very interesting. We had diffusion models were actually introduced in machine learning in 2015, so quite a few years ago. And then nothing happened for a couple of years, until the paper came out in 2020, where they made diffusion models more computationally tractable. And by that means is that you could basically train them and get some interesting results in finite time, in the sense that the original model that they invented in 2015, there were some academics, they were physicists and so on, it didn't really work in practice. It took too much time and it didn't produce good results and so on. But some academics, I think they were from Berkeley, in 2020, they made it more reasonable in sense of how to actually do it, and we will go through that paper a little bit in detail. Then we have some interesting papers coming up after that. So we have CLIP, which is an important part of this. It's a Facebook model for how to embed images and text in the same space and make them as close as possible. So that's an important part of how stable diffusion works. Then we had these latent diffusion models, which is a speed up. So you can make diffusion models and do them a lot faster. So it's important in terms of computation. And then we have these more famous models, which is DALL-E 2, April 2022. So that's in the spring. And then we have Google's Imagine in May 2022, and then Stable Diffusion in August 2022. So as soon as people started working with the denoising probabilistic diffusion models in 2020 and started making it work, and there was a lot of papers in between that I don't have here that actually made the computation works, suddenly everything exploded this spring, I would say, in the sense that there's a lot of stuff that people like churn out right now with these models. So it's a slow start, and then it's like a ketchup bottle that just spews out papers and changes here. But the basic technique is from 15, and then the 2020 paper is paramount as well. So that's the timeline. So the diffusion models, they work, so the original inspiration is from physics, where you have this process of diffusion, and you can see it to the right, where you have an image that you start adding noise to. So you add Gaussian noise, which is just white noise, and you suddenly add that onto the picture to make it more and more noisy, to make the flower harder and harder to see. And you diffuse the image until it becomes just pure noise. So that's what's called the diffusion process, just diffusing the image into noise. And then you have something that's called reverse process or denoising, where you start from something that is purely noise and go back to the picture. And it's actually mathematically, it's a Markov chain, because it's sort of just depending on the previous picture, and you add noise and add noise and add noise until you get pure noise. And then the reverse process is going from noise, less noise, less noise, less noise, less noise, until you get the picture. So you have the diffusion process, adding noise, and the reverse process, denoising, getting back to the picture. So that's the whole process, the essential idea. And you have these conditional probabilities, which is P, removing noise, and then Q, which is adding noise. And the model is actually then trained to remove the noise from the noisy picture. And there is some, it's from thermodynamics originally. This is where I sort of ended up in a rabbit hole, because you start with defining this this whole Markov chain with adding the noise, and it turns out to be, and what they did in the original paper is they derived this variational bound. It's just a mathematical expression of how you would optimize this chain, and it's in the original paper 15, it was super hard to calculate. They didn't approximate it, they just calculated. And then in the 2020 paper, they actually did a lot of approximations. These are these many pages of math, where they actually derived something that is more tractable, which is what we know from machine learning, which is this equation down there, which is that diffusion model and the models that you actually use when you generate these pictures is a model that is predicting the noise that has been added to the picture. So you have a picture that you add noise to, and the model is trained to come up with sort of how much noise has been added to each pixel of that picture. And then you try to subtract that noise and get back to the original picture. So that's what the equation down there says, that you have epsilon, which is the noise that is added to the picture, and epsilon theta is your neural network that is predicting the noise from a noisy version of the original image. And this is equivalent to training a model using backpropagation, what we usually do in machine learning, in order to predict the noise that had been added to the original data. And this is nice. It's a lot easier than just working with these variational techniques and stuff that they did originally. So, and actually it's funny that the model that this stable diffusion is doing is using the UNet architecture, which is also a really classical neural network that is, I mean, from 15 or something like that as well. People came up with in biology to predict, I think it's cancerogenic things in pictures, like cancerogenic cells in pictures. And this is what they did in 2020. So you actually came up with a version of predict the noise that has been added to a picture. And that's how it works. Which is basically what this stuff is doing here. You start with noise and then you predict how much noise has been added and you sort of end up with a flower. So yeah, you feed the model with a weighted sum of noise and image. So x0 here is the original image, and then epsilon here is the noise, and depending on where in the diffusion process you are, you have different amounts of noise, basically. So you can make it very hard for the model to predict a lot of noise, or you can make it easier when it's basically close to the final image, where it's a little noise. Okay, yeah, here's some code for that. So this is my favorite machine learning framework nowadays, which is Flax, based on JAX, which is functional version of a neural network training. But this is basically exactly what it does. You have a original picture that you sample some noise, and you make a weighted sum of the noise and the picture, and you get some target, and you train the model to reduce the, try to predict the noise. So here is the X is the original picture, here's the noise, and this is the weighted sum. And you can see that the target is the noise that has been added. XT, which is the weighted sum of the image and the noise, is what you feed to the model. So this is a forward of the model, which is XT, the noisy version, and then the loss is the difference between the target, which is the noise, and then you do backpropagation of that. So yeah, if you know machine learning code, it makes sense. Otherwise, it doesn't make sense, basically. But that's a general idea. But that's, I mean, this is just unconditioned image generation. You start with noise and you try to get the picture from that. But there's no way of actually adding text to that. So what people did after is that you actually condition the diffusion process with some text to say that from the noise and a text, you should generate the picture. And that is conditioning on text. And this is where this CLIP paper came in, and also the DAL-E2 paper, where basically so the CLIP Facebook paper is that you try to train a model, you have some text, in this case it's Pepper the Aussie Pop, and then a picture of this dog, and you try to train the model to align, okay, this text is about this dog. And you train the model with a batch with a lot of texts and a lot of pictures, and the model is trained to say, okay, which text belong to what picture. And by that, you learn a representation of both text and images that live in the same vector space. Basically, you can say that this picture of a dog and this text about a dog is probably about the same dog. And this is what they used in the DAL-E2, where they have, this is a dog blowing a trumpet that is burning, and you can basically learn a Corgi playing a flame-throwing trumpet. So you learn the model to say the Corgi playing a flame-throwing trumpet is the same thing as this picture. And then you can use the embedding when you do the diffusion process, so you add the noise, and this is the conditional probability here. You have the embedding of the text in this latent space, and then you try to generate the picture from the text and the noise. Technically, it's just you have the unit architecture, and the unit architecture is usually working on pictures, but then you also add the embedding of the text into the unit, and it tries to predict the final picture. Okay. So far, so good. I mean, we're going fast, but...
I have a question.
Yep.
How the data that these models have been trained on, what is the connection between the text and the image?
Yeah, so it's a good question. I don't have anything about this here, but actually these data sets are trained on data scraped from the web. So like OpenAI and Google and Facebook, they have their own data sets, where they basically scrape the internet, and you have, usually in HTML, you have this text prompt that you add to a picture in order for people that are visually impaired can get like a computer read the description of the text for you. So I think it's called alt text or something like that in the HTML code, yeah. And you can basically train the model on the image and the alt text. So that's what they did. And OpenAI, Google, and Facebook, they have their own data sets, but there are also an open data set called Lion. I think it's a German organization that has created a huge data set with exactly these pairs, image and text that you have scrapes from the web. So this is what you train on. So you start with the text from the alt text from the HTML and the picture, and you try to learn the model to predict the picture from noise and the text. These are huge data sets. In order to make this work, you need to train it on, vast amounts of data. Okay, so now we come to stable diffusion, which is, so the problem with this original diffusion model is that it takes a lot of time to do denoising of a high resolution picture, because you need to predict the noise that has been added to every pixel, which is a lot of computation, and it's also not very interesting, because semantically, different parts of the flower, there's different kinds of yellow or different kinds of green and so on, and spend a lot of computational resources to predict exactly the kind of yellow or the kind of green on the leaves is a waste of computational time. So what you try to do is that you try to do this, it's called perceptual compression, I think would be the word, that you try to remove everything that is just different aspects of colors and so on, which is not semantically important of the picture. The picture is of a dog on a field or something like that, that's semantics, otherwise it's just perception. And you try to remove that and get a semantic version of the picture in some other space. And then you do diffusion on that other space. And that's what latent diffusion is about and what stable diffusion is working on. So let's say, diffusion process in pixel space is extremely slow. So there was a lot of paper before latent diffusion came out. There was a lot of tricks to speed that up. But basically, what this algorithm is doing is that you take a picture, in this case of a cute cat, and you embed that into some space where the cat is just a vector, and that vector contains the semantic information in the picture, which basically it's a picture of a cat, with the paws on a sofa or something like that. And mathematically, it's just a vector. And then you do the diffusion process in that latent space instead. And now, this is where you need to be machine learning engineers to understand this picture. But basically, so the funny thing here is that it's a lot of parts. Machine learning nowadays is it's a little bit like you have a toolbox with all these different models that people have trained before, and you put them together in something new. And this is exactly how this works. So stable diffusion works by two autoencoders. First, you have an autoencoder that can put your image into this latent space, where it's just a vector, where you have the semantic meaning of the cat preserved, but maybe all the perceptual differences in colors and so on removed. And then you have a denoising autoencoder that takes a noisy version of your picture and removes the noise, or a noisy version of your latent representation of the picture and removes the noise. So that's 2 models that you need, and then you have 2 more models. It's actually this text and image embedding that you want, and this is the clip embedding that they use in Stable Diffusion, which is that if you're conditioning the diffusion process on a text, you need to embed that text into a vector and then feed the model with that text. So basically you have a latent representation of your picture and you concatenate that with the latent representation of, or a representation of the text, and you feed both of those into the UNet and tries to predict a new representation which is less noisy. And
you add noise to that first representation you have.
Right, exactly. Yeah. So you start with, so the diffusion process is basically you have your original picture, which is the picture of the cat, and you embed that into your latent space, and then you start adding noise to that. So you get this Markov chain of noisier and noisier and noisier pictures until you get completely white noise picture, or latent representation of the picture. And then the model is trained to remove the noise from the latent representation of that. And then you get something that the model is thinking is all the noise is removed from this latent representation, and then you take the autoencoder to decode it back to image space, which is when you get the final picture. And then you condition that. And the funny thing with the latent diffusion is, of course, you can condition it on all the kind of modalities. Modalities is just different kinds of data. It's text or images, basically. And the good thing with clip is that it can embed both images and text. So you can condition the model on a text, or you can condition it on an image. We will see examples of that later. So, and the good thing is that they have the same representation in the latent space. Right. So here, this is also a little bit of a rabbit hole discussion, but basically the UNet is the standard neural network where you start with a high resolution version of the picture and you make it more and more abstract, and then from the abstract representation you get into something more and more realistic. And this is a little bit where it's a toolbox kind of problem, where you have attention, where the different parts of the UNet can look at different parts of the prompt that you're conditioning it with, just for the model to understand that, okay, now I have a representation of a cat, and my text is a cat playing a trombone. Maybe at some part in the process it needs to care more about if it's a cat, and at some point in the process it needs to care more about that it's a trombone that is sort of adding to the picture. So the model learns to attend to different details of the picture in different parts of the process, which is why you use attention. Right. But okay, now we come to, now we just have some examples of how this works. But before we go into that, maybe there are some more questions of exactly what the model is doing. Yes?
I'm using clip to kind of turning pictures to text in order to learn to prompt engineer better.
Mm-hmm.
But then so when you say it looks at different parts of the text, is that kind of a feasible way to go, or? I'm taking pictures and putting them into clip to let that convert it to text prompts.
Right. Yeah.
Under the assumption that if I can learn how clip translates picture to text, I can convert and get DALL-E to be better.
Yeah. I think that makes sense.
I also used D3 to write prompts for DALL-E, which is...
No, but they are completely different architectures. And
it put out some really bizarre text and characters that got splendid results.
Mm.
So,
I usually call these models a little bit of voodoo magic in some sense. Maybe that works, maybe it doesn't work. I cannot really tell why it does.
It would fantastic.
Okay, yeah. Maybe that's voodoo, maybe that makes sense. Who knows? But I would say that using clip to decode the image into text makes more sense than using GPT-3, because it's more reasonable to assume that the text that you would get from an image using clip the whole way makes more sense when you're using stable diffusion. But of course, these are all the same. These are all transformers. So, and transformers probably represent the text in the same way. So there's probably some generality in how GPT-3 thinks about text as Clips thinks about text. So, right. Any more questions or comments?
Super interesting.
So, right. But the thing is that you can do a lot of, I mean, people are doing a lot of crazy stuff with these techniques right now. So one thing is in-painting. So I want to explain a little bit how these different things work now when we know the basics. So in-painting is basically, I have a picture here, which is a lady in front of a fence, and I draw a line around that lady. I want her to be removed, and I would just want to get the fence back. So the way that you do that is that you train a model on the mask, sort of, and here I have some celebrity probably, don't know who, but you train the model and you're adding the mask, and you make the diffusion process sort of conditioned on the picture and the mask. You ask the model to reproduce the original picture. So you work this diffusion process where you start with noise and you learn the model to remove more and more noise while telling the model that I have this mask and you're supposed to fill in something else for the mask. So you can, and you basically train it on these kind of pictures. That, yeah, I have these ladies or these black blobs that I want to remove, and you train the model to reproduce the fence, the pure fence, or the pure. So what is happening here is basically that I have the noise added up here, and I add the mask down here, and the model is trained to reproduce a picture with something else inside the mask. So that's in painting. I know, like Adobe is trying to implement this in Photoshop and so on, because it's super useful for artists to just draw a mask around things and then you get rid of that thing and you get like the picture without that mask. I think that maybe they have already done it. I know. Yeah. So, and then we have another funny thing, is that you can condition the diffusion process on a semantic map, which is that I just have drawn something. I have some gray stuff here, I have some red stuff here, and some green things here. And you add that as your conditioning to the model. And the model is then trying to create a picture. These are different scenarios. So here you train it. I think there is also a public data set here that you can use. I don't remember the name of the data set, but it's from a web page with landscape pictures that you can train the model on. And then the thing with the latent diffusion is that the reverse process to removing noise is stochastic. So you would get a different image every time, which is why with the same, because of this noise that you add in each step from the training and from the forward process it makes it stochastic, which is why you get these different pictures every time. But basically it's the same idea. You just condition it on the semantic map and you train it to reproduce the landscape. So the third example that I had was something is called super resolution, which is classic. Do you know this time, the TV series? I think it's CGI New York or something like that, or CSI New York, something, where you have this enhance, and they can draw a picture on the video, and then you say enhance, and they get like an enhanced version of that. So in that TV series, of course, you can put it on the front plate of the car, and you can see the model would reproduce the actual number of the car plates. So this is actually not how this model works, but it's getting close. So you start with a low resolution version of this man, and the model is then trained to make a high resolution version of it. So in this sense, in this version, what you feed the model here, the t theta, is the low resolution version of the picture, and the noise that you add is high resolution, and you add the model to reproduce a high resolution version. So here is just an example here that I have this noisy version, which is a low resolution, and the diffusion process is then trying to make the full high resolution version of the picture. Right. So all these three examples, it's exactly the same architecture. You just use different data sets to train it with, and you prompt it with different kinds of pictures or texts. Right. So, I mean, I think the final slide I have is just how this is different from GANs, Generative Adversarial Networks, which was the state of the art before. And we had a meetup in the association about that a few years ago. Marco did that. And we highlighted a couple of questions here. So why diffusion models is actually better than GANs in doing this. So the first thing is something called mode coverage. And that is, I mean, if I give the model that it should produce images of dogs, mode coverage means that a GAN can only produce images of, let's say, standing dogs. Why this kind of model can also produce pictures of lying dogs or running dogs or sort of playing dogs or something like that. That's what technically is called mode coverage. That you have different kinds of modes where the dog is working. And GANs are trained in such a way that they are really bad at doing that. They can basically just do standing dogs or sitting dogs or something like that. But it's very hard to make them all kinds of dogs. GANs also suffer from a problem that is training complexity. I mean, they are very hard to make converge. You have to spend a lot of time making them converge. So building these models takes a lot of time from the machine learning engineer. And diffusion models is a lot easier to train, which is also why they are like churned out every day, new versions. The big problem with diffusion models is that they take a lot of time to create new pictures. Because this diffusion process where you remove the noise is that it removes very little noise at each step. So to get from pure noise into a picture takes like, okay, in the original paper they had 1,000 iterations. And if you do, like every iteration takes half a second, you know that you're already in a spot in getting a lot of pictures, while GANs is faster. But this is what people are sort of working on to improve. So you should be able to get these pictures in a lot faster. Right. So we just had a discussion at work a couple of hours before I came here. We had a client that wanted to do GANs. And the standard answer from now should be, don't do GANs anymore. Do diffusion models. Yeah, sort of that's explaining stable diffusion as if you were a machine learning engineer in half an hour, approximately.
Very cool. But DALE, is that the diffusion?
Yeah, so there's a difference between DALE 1 and DALE 2.
Yeah.
DALE 1 was not the diffusion model, while DALE 2 was.
And Midjourney is also diffusion.
Midjourney is diffusion and Imagine is diffusion.
But Imagine is not available for public.
No, and DALE 2 is not. I mean, you can use the API, but the code is, and the weights are not public. Stable diffusion is the only one where they actually have published the weights, which is why you have such an explosion in applications. Yeah.
Very.
Yeah, I mean, it's definitely the stuff that you read in newspapers, and then.
So just application of a different thing. I read an Indian research team. They had used it on to get predictive or predict buying behaviors of different consumer groups. So they basically let they use a GAN
Yeah.
and let it predict first product groups, and then buying groups, and then they could predict like middle-aged moms would buy like teenage hoodies or BMX bikes, or opposite kids would buy, you know, carrots or whatever.
Mm-hmm.
Like unlikely combinations. I think it was super.
And they use diffusion models for that?
Yeah.
Okay.
No, not diffusions. Generative.
Okay. Yeah, sure.
Have you seen any other applications? Because image and voice and stuff, it's super common, but more generational thing.
No, well, I think the example that you given, it's a little bit like if all you got a hammer, everything looks like a nail kind of approach.
Yeah.
Because it's a little bit like that you would be able to solve like with a recommendation system that has been around since the 80s.
Yeah, and that was their, they said that probably Amazon's recommendation systems are as good.
Yes, or better,
Yeah.
most likely.
Yeah.
Yeah, so that's why it's a hammer and nail problem. But generating data sets is kind of a big issue here. So getting annotated data and synthetic data and so on, it's a big problem for a lot of companies. So, I mean, it probably makes a lot of sense to do synthetic data generation with these kind of generative models. That I think is the most reasonable application that I've been.
So then you have Palm and those huge models, but then you have the GATO track as well.
GATO track.
Yeah. It's a small, super generic model that can kind of recognize pictures and control a robotic arm with the same weights.
Okay.
Okay.
No. Are you talking about the Deep Minds model? Yes, GATO. Yeah. I know this one. But okay, that's actually reinforcement learning.
Okay.
Yeah. So it's not a generative model. It's the GATO model is. But it's also very interesting, of course. But that model is trained. It's a transformer architecture where you can work on different modalities, which is someone playing an Atari game, some text, some images, and exactly. Yeah. But then it's just trying to predict what's going to happen next, and it's using reinforcement learning to do that. So it's not a generative model in the sense that you can just generate data or dream up data, but it's predicting what's going to happen next. Which is a discriminative model instead of a generative model. Okay. Thank you for good questions.
Super interesting.